As we prepare for the fall semester exam, I'm going to take and break down by unit of the topics that we've covered this semester so that we can have a comprehensive review. This video will cover the topics relating to the nucleus. You'll recall the atom is made up of a nucleus containing the protons and neutrons, which is where the bulk of the mass of the atom is found, surrounded by electrons. We'll talk about electrons in the next video. But there's some things that we know about the ratios of these particles in atoms. That is that the atomic mass is made up of the number of protons and neutrons, and when the number of neutrons vary, we call that an isotope. For example, a sample of carbon-12, the atoms will have 6 protons and 6 neutrons. But a sample of carbon-14, an isotope of carbon with a mass of 14, will have 6 protons and 8 neutrons in the nucleus of the atom. For balanced atoms, the numbers of protons and electrons are generally balanced. However, if they are not in balance, then that is called an ion. An ion can be positive if there are more protons than electrons, or an ion can be negative if it has more electrons than protons. To make the point about ions, let's consider the isotope of oxygen-16 with a mass of 16. Its number of protons is 8. It's a neutral atom of oxygen with 8 electrons. But what if the number of electrons is 10? In that case, this isotope of oxygen actually has a charge of -2 because there are 2 more electrons than protons. Likewise, if we had, say, fewer electrons, maybe 6 electrons, then we have an imbalance of protons and the charge would then be +2. The atomic mass is a number found on the periodic table. It's the decimal number. It is the weighted average of all of the isotopes of an element. This number is always rounded to the nearest hundredth, or 2 decimal places. For various isotopes, it's helpful to use abbreviations like hyphen notation or nuclear notation. Hyphen notation is when we use the element symbol, such as carbon, a hyphen, ironically, and then the mass number, which is not the atomic mass with 2 decimal places, but is the mass expressed for that specific isotope. The nuclear notation demonstrates both the mass number as well as the atomic number. The nuclear notation gives us information about the contents of the nucleus. Nuclear notation is also the form that we use when showing the nuclear decay equations. If we were demonstrating a different isotope of carbon, then it would have a different mass shown, and that's how we would know the difference between the isotopes. With nuclear notation, it's set up as a beautiful little math problem for us so that we can calculate the number of neutrons. Since the top number is the mass and the bottom number is the atomic number, meaning number of protons, then we can subtract those to get the answer for the total number of neutrons. Since the neutrons and protons together, the 8 neutrons and 6 protons, make up the total mass for that isotope of carbon, 14. We have discussed 3 types of radioactivity, which is the nuclear decay of an atom to become a more stable atom. This decay can occur by alpha radiation, which equates to a helium nucleus, beta radiation, which is a negative particle, or gamma, which is simply a form of energy being emitted. We don't have any equations for that because it doesn't change the mass of anything. But just to know that energy can be a product of radioactive decay. We can use the alpha and beta particles in nuclear decay equations to show how an element breaks down. If we want to demonstrate the alpha decay of a uranium-238 radioactive particle, there would be, because it's alpha, an alpha particle coming out, and then we have to do the math to figure out what particle makes up the difference mathematically. What plus 2 equals 92? That would be a 90. What plus 4 equals 238? That would be 234. And then we look up element number 90 on the periodic table to find that it is TH. And that would be a nuclear equation for the alpha decay of uranium-238. What if we want to show the beta decay of uranium-238? In this case, we begin with the same isotope of uranium as an example, and we now need to do the math to figure out what particle plus a -1 would yield an answer of 92. That would be 93. Adding 0 changes nothing, so the top number remains the same, and then we look up element 93 on the periodic table to find that it is Neptunium, and that would be the nuclear equation for beta decay. Notice that these numbers, 90 and 92, add together, and the numbers 234 and 4 add together to make 238. Likewise, in the beta decay, 238 plus 0 is 238, and 93 plus a -1 is 92. Half-life refers to the period of time that it takes for a radioactive sample to decay to 50% of its original sample size, or reduced to half. For each half-life, the sample is reduced by half each time. This can be expressed in terms of grams, percentage, or as a fraction. The point is to count the number of half-lives. So, for example, if the half-life of a sample is 1 day, that means that half of the original mass will remain after 1 day has gone by. Okay, what if we had a sample of 100 grams and it had a half-life of 1 hour? That means that after an hour, there would be only 50 grams left. That's 50% of the original sample of 100. So after the first half-life, you have half the original mass. At hour number 2, there would be only 25 grams remaining, because after the second half-life, there's only 1/4 of the original mass remaining. And so on. You can take the mass and divide it by 2 each time. You can take the fraction and halve the fraction. But you should be able to count half-lives through periods of time to figure out how much of the original sample remains. Molar mass is the mass of 1 mole of an element or compound. The mass on the periodic table is the molar mass for each element. Molar mass is always expressed to 2 decimal places. So if I'm looking up the molar mass of something like oxygen, oxygen is one of the diatomic 7, so there would always be 2 atoms of oxygen in that molecule. I would have to multiply the mass of oxygen, 16.00, times 2 to get the total mass of that molecule, 32.00 grams per mole. I can also do this for more complicated molecules, like this one. First, you have to figure out how many atoms of each element there are in the compound. The formula here says Ni3, PO4, 2, meaning there are 3 nickel atoms bonded to 2 phosphate polyatomic ions, and each one of those is made up of a phosphorus and 4 oxygen. So the total tally is 3 nickel, 2 phosphorus, and 8 oxygen, since the phosphate molecule is doubled. If we look up the molar mass of each element, nickel, phosphorus, and oxygen, and add together the total quantity of each of those, we get a final answer of 366.01 grams per mole for that molecule. It's important to remember that we're simply adding all of the atoms in this molecule. We add together 3 nickels, 2 phosphorus, and 8 oxygen to come up with the total. A little bit of multiplication can be used as a shortcut, but don't be confused. It's not a multiplication problem. It's an addition problem. We can use molar mass, which is the ratio of grams per mole, to convert to number of moles, to number of atoms, to grams even, we start with the understanding that a mole is a quantity. It's Avogadro's number of 6.02 times 10 to the 23rd. Atoms if we're talking about elements, molecules if we're talking about compounds. On your review guide, as on the semester exam, there are problems where you will have to take number of moles of a substance and convert to the mass of the substance. We use molar mass of grams per mole as a conversion factor to make that happen. Here are two of the problems worked out for you. Notice that the conversion ratio is set up so that moles and moles cancel, and the final answer is expressed in grams. Notice that the final answer is rounded to the number of significant digits to match the significant digits given in the original problem. As you go a little further into your review, you'll come across problems where you need both molar mass and Avogadro's number to come up with the answer. In this example from the review guide, you'll see that grams of sodium chloride were given, and the question was number of molecules. So first we use molar mass to convert from grams to moles, and that comes from the periodic table. Then we use Avogadro's number to convert from moles to molecules. Multiplying across the top and dividing across the bottom yields the final answer of 1.03 times 10 to the 23rd molecules. You can ignore that the answer key says atoms, when clearly NaCl is a compound and that would be molecules, and that was the question being asked anyway. So, little typo in the little answer key. I hope that you've paid attention. If you have watched this video all the way through and paid attention to some of the example problems that I've worked, you've actually seen some of the questions from the final exam. If you can do these, you can answer those questions on the exam correctly. Study well, and best of luck.